Welcome to the Spectral Geometry Seminar, Spectral Geometry in the Cloud Seminar. This week we have the immense pleasure of having Nilima Nigam from Simon Fraser University, which will speak about approximation of Laplace Steklov eigenvalues. The stage is yours, Nilima.
Thank you. Thanks everyone for coming out, and a very special thanks to both Jean and Alexandre for organizing the spectral geometry in the clouds. I don't know about anybody else, but this has been something that has kept me quite sane through this pandemic. So it's been a service to all of us. All right, so I'm glad to be here. And I was going to talk to you about not just my work, so mostly, in fact, other people's work, about the approximation of Laplace Steklov eigenvalues. So this is a crowd that knows way more about the analysis of these problems than I would claim to. But I thought I would show you or share with you some ideas and perspectives on how to compute these objects. So some of the work I'll present today is joint work with Elar Ahmedgaliev, Oscar Bruno, Nurbek Tajenbetov, Habib Amari, and Thime Mary in various aspects of the projects. All right, so just to fix notation, I'm going to be interested in a couple of planar Steklov problems. The domains omega will be bounded and Lipschitz. The Steklov eigenvalue problem has Steklov parameter lambda j. And the sloshing Neumann eigenvalue problem, um, I would have the spectral parameter, again denoted by the lambda j, on part of the boundary, and the Neumann trace would be 0 on the rest of it. Whoops. So what I wanted to go over fairly gently maybe is a motivation as to why I'm interested in using boundary integral methods for these problems. And I'll try and describe how it works for smooth domains as well as on polygonal domains, and then the harder, to me, the harder problem, the sloshing problem. And throughout, I'll try and emphasize some simple relationships between um, the numerics that we're able to do, how we might decide that we're doing a good job, how we might aid our colleagues in analysis in coming up with um, informed conjectures based on numerics. And this is quite a delicate business because it's easy to generate pictures. We should all be suspicious of pictures, which we rightly are. But in some cases, the pictures help those of us that are trying to actually compute. But more than anything, what's been helpful for me has been a series of papers that have come out recently from many of the people on this seminar right now, because they allow us to validate what we're doing. All right. Whoops. So how I got interested in this problem, my initial interest was piqued by the 2012 Ig Nobel Prize, which was awarded in fluid dynamics for the dynamics of liquid sloshing. So what happens when you walk with a cup of coffee? And I thought this was quite an amazing paper. And that's where I first realized that, okay, there's an interesting eigenvalue problem here. Of course, there is an interesting eigenvalue problem. All of you knew that. I did not. But more seriously, I got very, very interested in these problems due to a sequence of conversations and papers that I read from Alexandre Girouard and Josef Polterovich. And this, I think it's been maybe a preprint since 2014, but appeared later. So this was the review paper, if you will. Then there was a very nice set of work by Girouard, Parnowski, Poltrovich, and Scher on how the asymptotic behaviors of the Steklov spectrum on smooth domains might go. And this to me was quite striking, and I'll describe why I found this to be a challenge, if you will. So this stuff led me to think about computing Steklov and sloshing modes. And in this review paper from the notices of the AMS, there's very nice pictures. I think you're all familiar with it, so I will not belabor it. And somewhere along the line, there's also this business of the plasmonic eigenvalue problems, which are in fact quite, I would say, hard. Um, and the person that does these really well, maybe he's going to be here today, or there are several people that do this really well, but numerically, I think it's hard to beat the work of Johann Helsing on this. All right. So just again, what's going on here is, as you all know, if we've got the Steklov eigenvalue problem and we think about the harmonic extension map that takes us from h1/2 objects on the boundary into the unique harmonic extension, which would be in h10, and you denote by d minus the Dirichlet-Neumann operator, then the spectrum of d minus is precisely the Steklov spectrum. Now, I I started out thinking about this stuff and believing that, okay, for Steklov, I should be able to handle smooth domains and polygonal domains no problem. The challenging stuff would happen at the Steklov-Neumann boundary. And so actually, paradoxically, I started thinking about the Steklov-Neumann problem first, or the sloshing problem first. And so what happens at the junction of the Steklov and Neumann data? That would be of interest when you're doing numerics. So there's this paper by Kondratyev that shows that if you're solving a boundary value problem with mixed Steklov and Neumann data, then at the corner, you do pick up some asymptotic behavior. And so this can be well characterized by looking at certain weighted Sobolev norms. And so this was the first inkling that I had that, okay, we will have to be very, very cautious near the junction. In terms of the eigen problem, though, there's a very nice paper by Komarenko from 1980, and I did not originally have access to the translated version, and this is something that Eldar actually translated for me. So if you have a domain such as the one I've shown here, where you have, say, Steklov on the red pieces of the polygon and Neumann, pure Neumann on the blue parts, then close to the junctions, the eigenfunctions have a certain regularity which depends on the nature of the angle, right? And so what is this? Well, here's a screenshot from the paper by Komarenko. His expression was really horrible, actually. So he writes out the asymptotic expansion of the eigenfunctions, and the gist of it is that you will have possibly some fractional powers of the distance from the corner, as well as some logarithmic terms. Right? So more precisely, this is what he stated. So he said that if you're getting close to the junction, then depending on alpha, the opening angle, you will have the distance to the power j over alpha, uh, or if you have certain rational multiples of pi, then you will have both polynomials in the distance and the log. And if your angle is rational but not of the special form 1 over m, then you have both the logarithmic and fractional singularities. So this was old work, um, but this was a cautionary tale for me right off the bat. So you have many options when you're numerically approximating eigenfunctions. As we all well know, you could approach things in a variational manner, or you could do it on a collocation approach. So a variational approach would be, for example, a finite element method or a boundary element method. A collocation approach would be something like the method of particular solutions, or the approach that I'll talk about today. You could do a domain-based method. You could do a boundary-based method. What sort of discrete spaces should you use? Should you use polynomials or should you use other approaches? There's a very nice recent approach that Nick Trefethen is advocating in terms of rational polynomials. No matter what you do, your choices are going to be informed by the twin objectives of maintaining accuracy of your discretization. You wish to approximate the eigenvalues and eigenfunctions accurately, but also conditioning. And this is a subtler problem, and I will hope to illustrate it without precisely defining it. But conditioning is often where, when we try to get very, very high accuracy, we can do this on paper. As in, I can write down a discrete scheme that on paper looks really good. But then when I implement it in finite precision, the objects that I get are quite sensitive to small perturbation or rounding error. And that's usually a signature of conditioning. It's not accuracy, it's conditioning. One might also ask, okay, so we know that for C2 boundaries, things will behave rather well. So do you have to do something complicated there or not? If you're using a finite element approach and you're going to be discretizing with, say, triangles, but not curvilinear triangles, should you approach the C2 boundary situation with those meshes, or should you use isoparametric finite elements? And finally, as I said, sort of approach this backwards. I started to think about what happens at the Neumann-Steklov junctions, and so how do you incorporate that into a numerical method? And many of you have seen this slide before. I like to show it just to fix my own ideas every time. So the problem that we have, and I'm not sure, can you see my mouse or my cursor, Jean?
We can, it's
Yes,
Alex.
yes, yes, we
Okay,
can.
great. Okay. So I have options on how to formulate my eigenvalue problems, right? So I can formulate it at the continuous or the infinite dimensional functional level as some operator A acting on U equals some spectral parameter B times a different operator acting on U. And the goal here is to locate sigma and U. But this is not what I actually compute. What I actually compute is in a finite dimensional function space. So I have to come up with some approximation space H sub n. Ideally, H sub n would be a subspace of H1. Doesn't have to be. If it's not, it's a non-conforming method. But at any rate, once I'm done writing down a finite dimensional function space, I reformulate this problem, AU equals sigma BU, as a problem in a finite dimensional space. So, and I'm missing a B here. So I denote by the operator in the finite dimensional space A sub n and the associated eigenvalue is sigma sub n. So this is where typically the analysis occurs for numerical analysis. But again, this is not what you actually put onto your computer and ask for an eigenvalue. What you would do is to convert this problem by picking a particular basis in your H sub n and then reformulating a generalized matrix eigenvalue problem. So you get some sort of a matrix A and M acting on a vector UN. Um, and then here you have another matrix B and M acting on UN, and then you're trying to locate the sigma n and UN. Now, this sigma n here, if you've done this well, this should be the same as the sigma n above, but it doesn't have to be. Because again, this depends on how you pick your basis in your finite dimensional space. And then finally, you have a generalized matrix eigenvalue problem or a pencil problem, and you try to compute it, but you cannot get your hands on even these eigenvalues precisely because you have to do something iterative, right? So you're going to be computing the eigenvalue problem using some sort of an iteration, and then you will also incur um, errors over there. And it has been my experience that the conditioning of the problem becomes an issue when the matrices A and B that you generate at this step right here, when those become ill-conditioned, it becomes very hard to trust the objects that you start to get here, even though the accuracy issue, as far as I'm concerned, relates what you're getting here to what you're getting at the infinite dimensional level. Okay. All right.
Excuse me. Uh,
Yeah,
can I ask you, is B really acting into different space than A?
it could, but in our case, it doesn't.
So if sigma is just a scalar, so there is some sort of embedding between them assumed, or like
Yes,
how they,
yes, of
okay,
course, of
okay.
course, yes. There
Thank you.
has to be. Otherwise, you can't formulate an eigenvalue problem, right?
Right.
Yeah, yeah. All right. So I'm going to blast through this. There's a considerable literature in the numerical analysis if you look for the word Steklov. Okay. Um, there's a partial list of papers right here. And a lot of it originated with, on the one hand, the finite element literature, and on the other hand, the discretization of integral operators. So on the finite element side, a lot of the attention was dedicated to what was called the Steklov problem, but it's actually not for the Laplacian, it's for the shifted Laplacian. There's some very sophisticated work still ongoing, including a posteriori estimates, adaptive methods, eigenvalue enclosures. So there's a lot of very, very careful work being done on the finite element side. Um, on the integral operator side, there's again a considerable literature on how to discretize boundary integral operators. And there's work that dates back, say, for the boundary element approaches, which are Galerkin approaches for integral operators, to the works of Shaw and Wendland from 77 and even earlier. There's very nice work by Costabel and Stefan on what happens if you use these integral operators on curved polygons. What I'm going to talk about today is motivated highly by the Nystrom collocation approaches that are due to Kress in 89 or Colton and Kress in 83, even earlier. Um, this work has spawned its own thread of research. So integral operators have been discretized very carefully and studied very carefully in the collocation sense by Atkinson and Sloan and others. The spectrum of layer potentials, I have to highlight this. This is some beautiful work by Johan Helsing and Carl Michael Perfect, in which they have done what I consider to be a very hard problem. So they're looking for the plasmonic eigenvalue problems on domains with corners. And if you're looking for a very nice way to discretize operators with very sophisticated quadrature schemes, I can't recommend highly enough the work of Helsing from 2013. He calls it a tutorial, and it's what he denotes the recursively compressed inverse preconditioning for second kind boundary integral equations. But you can use these techniques. In what I present today, I have not used these techniques, but this is, I think, a very promising approach. All right. So why did I opt to go with an integral operator approach? Um, so we know that, of course, the Steklov problem has nice features when you're on a smooth domain. So for example, you have a discrete spectrum, you have no finite accumulation points, you have some sanity checks, so you can look at the high frequency eigenvalues, you can count how many are before a given lambda, and you can see if it's scaling at least to first order with perimeter. You can write down the Steklov eigenvalues and eigenfunctions for some very specific domains. So for example, on the unit disk, everyone here, of course, knows better than me that you can write down the eigenfunctions as r to the j, where r is the radial parameter, times e to the ij theta, where theta is the angular parameter. And here on the top row is just, for comparison's sake, the Dirichlet eigenfunctions, and on the bottom are the first few um, Steklov eigenfunctions for the same eigenvalue number, right? And what you can see as you go from left to right, at least for the circle, is that the eigenfunctions are appearing to concentrate near the boundary. And they will decay quite fast away from the boundary, at least for this case, because of the presence of this r to the j. And this suggests that if you're using a volumetric discretization scheme, well, then you're going to have to try to resolve quantities that are very small in the interior. But a lot of the variations happening closer to the boundary, and as you go higher into the spectrum, that concentration is getting closer and closer to the boundary itself. So an adaptive finite element is actually more suitable. Um, Another thing which is, I think, quite different from the perspective of computing is that the Steklov spectra for a disk, for example, well, you have one single eigenvalue and then you have pairs, right? And this is very nice. But then when you go to something like a smooth domain that's not a disk, then even though the first few eigenfunctions look quite different from the Steklov eigenfunctions of the disk, this very nice work of, I guess, David Scher and Josef Polterovich and Parnowski on the behavior of the eigenvalues of smooth domains as compared to the disk of the same perimeter, it shows you that if you're just looking at the spectrum, it's going to be very hard to distinguish between the spectrum of the kite and the spectrum of an equal perimeter disk. So you really want to do a very careful job of computing eigenvalues if you can. And so the result that I was just alluding to is this one, right? So it becomes very, very difficult if you're working with smooth domains to distinguish the higher eigenvalues from the higher eigenvalues of a disk, if at all. Even at the lower eigenvalues, the variation can be quite small. So you want really to get as many digits of accuracy as you can. So in this approach, or in this work, I use integral operators. And then sometimes I get a discrete nonlinear problem, but usually I get a linear problem. And then for the pure Steklov problem, I'm going to use something called a QR iteration. And for the mixed Steklov-Neumann problem, I use something called a QZ iteration. So one integral equation formulation or one integral operator formulation is as follows. I'm going to use a single layer ansatz, or I could try using a single layer ansatz with an unknown density phi. So I write down my eigenfunction u as the convolution of this density phi with the fundamental solution of the Laplacian. And then I define integral operators, so the single and the adjoint double layer, which I name S and T. I use the jump relations, so I'm not working with crazy domains. I'm working at most with polygonal domains. And the jump relations give you that you have continuity of the single layer and the double layer jumps by an amount that depends on the angle at that point. So usually it's a half if you're on a smooth domain. The ansatz that I've used is cleverly chosen because in this way, I make sure that my eigenfunction is harmonic in the domain. And if I enforce the appropriate boundary conditions, then I get an eigenvalue problem that lives solely on the boundary. So I have the double layer plus a half times the identity acting on the eigendensity is the spectral parameter lambda times the single layer on the density wherever you have the Steklov boundary, and it's zero otherwise. So what I achieve by doing this is converting a volumetric eigenvalue problem into an eigenproblem for the integral operators and an integral density. So I solve for the unknown density phi and eigenvalue lambda. Unfortunately, this approach doesn't really work. And the reason it doesn't work is that the single layer is not injective unless the domain has analytic capacity away from one. And it shows up very much and very quickly at the discrete level. So instead, what we do is we use a modified single layer. So I add and subtract a mean value. So I essentially factor out the kernel of the single layer. And the modified single layer operator, S tilde or S sub naught through my talk, this operator is injective. And so the eigenvalue problem that I actually solve is to find a lambda and an eigendensity phi so that the double layer plus a half acting on phi minus its mean is lambda times the modified single layer acting on phi. And the modified single layer again is the single layer acting on phi without the mean plus the constant. So I reduce the eigenvalue problem to this abstract eigenvalue problem here at the continuous level. So A phi is lambda B phi. Note that when I'm computing here, I will get the eigenvalues. I won't get the eigenfunctions. I'll get eigendensities. But if I wanted the eigenfunction, I can reconstruct it wherever I wish just by plugging it back into the ansatz. So if I'm working on a smooth domain such as this star-shaped object here with an outward pointing normal, then provided I have a pure Steklov problem, the problem that I'm working on is exactly this. So it's the double layer plus a half acting on phi minus phi bar is lambda times the modified single layer acting on phi. And then we can get into the gross details. So how do I actually compute these integral operators? So the very first thing I need to do is to parameterize the boundary. So I introduce a smooth parameterization, and my parameterization operator or object varies from 0 to 2 pi. And then I can rewrite the integral operator problem as an integral operator problem on 0 to 2 pi, where I've made explicit use of the parameterization. And the parameterization plays an important role because I pick up an extra factor of essentially the Jacobian of the transformation. And this will ameliorate any issues that I have due to the singularities. So I have the singularities of the double layer and the singularities of the single layer, the fake singularities of the double layer. It's not really singular. Because if you look at this very carefully here, done out with gory details, if you have a smooth parameterization, then for the double layer, everything can be written out very nicely. For the single layer, you can add and subtract the log of a sine squared of just t minus tau. So everything involving the parameterization goes into this object P. This part P is very smooth. And the actual logarithmic singularity you can characterize just by the log of the sine essentially of t minus tau, where t and tau both run from 0 to 2 pi. So this is very nice because it allows me to work with a large number of boundaries without having to design something special for all of them. As long as I can do a good job of the logarithmic term here, everything else is as smooth as I might want it to be. So on the matter of this logarithm, you can write down exactly what a good quadrature scheme might look like. And this is due to the work of Kussmaul in 69 and Martinson in 63 even. You can put it all together. And then the error for the Steklov eigenvalues computed this way will decrease spectrally with the number of discretization points or the collocation points that you put on the boundary. So this is very nice. Okay. What do I mean by this? So I know, for example, that on the unit disk, the true eigenvalues are 0, 1, 1, 2, 2, and so forth. The eigendensities for this problem will form a trigonometric basis. And if I apply the strategy I've just described, and I compute the errors of the first 16 eigenvalues, so I take the relative errors of the first 16 eigenvalues, I add them all up, then as I increase the number of discretization points, the errors are on the order of 10 to the minus 15. So the eigenvalues are being computed to extremely high accuracy, even with 32 boundary points, right? And the boundary traces, as I said, going from 0 to 2 pi in this parametrization, the traces are exactly, or the traces are exactly the trig polynomials, which they should be. So this approach that I've just described is extremely accurate when you're working with very smooth domains. For a kite-shaped domain, so which is something that is a perturbation of a disk, essentially, and a fairly large perturbation in this example, again, I can compute the first 16 eigenvalues. I don't know true eigenvalues anymore, but what I can do is compare the eigenvalues I've just computed with a highly refined calculation. And once again, with about 50 discretization points on the boundary, the sum of the errors of the first 16 eigenvalues is down to 10 to the minus 10. And these are the relative errors, right? So I'm adding relative errors for 16 eigenvalues and I'm getting 10 digits right there. By the time you've got about 64 points on the boundary, your errors are 10 to the minus 14, which is remarkable for a numerical method. So this is a very inexpensive, very efficient technique. Um, but then I was very curious about um, what's going on again with this very fast approach to the eigenvalues of a disk, right? So if I took a bunch of different kites shown on the left and I compute their first few eigenvalues, then I know there's this theorem from 2013 that these eigenvalues very rapidly approach the eigenvalues of the disk. And so on the left, you see the curves and the associated kappa. The kappa is the parameter inside the parametrization. On the right, you see the relative deviation from the quasi-mode. So the quasi-mode is what I'm calling the eigenvalues of the disk of the same perimeter. So you can see that by the time you've got an eigenvalue number of about, I don't know, 100, the kite in which the kappa is 0.1, those eigenvalues have become pretty much identical with those of the disk. As you increase the kappa, so say look at the cyan kite. This kite it doesn't look like a disk anymore, but if you were to compute its eigenvalues, the eigenvalues are going to go down, but they will go down to machine epsilon compared with those of the disk further out in the spectrum. All right. So I thought this was interesting. So this approach that I've just outlined and the solver was used by Ahmed Galiev and Kao and Austin in 2015 to do a spectral optimization for domains with smooth boundaries. So they were asking specifically what happens if you're trying to maximize the pth Steklov eigenvalue with a fixed perimeter. So they showed that at least numerically, you have p-fold symmetry and the maximizers are unique. And so shown here are some of the shapes that they obtained through a maximization process. And here are some of the domains where you take p to be an even number. So you have this multiplicity structure, but you also have this p-fold symmetry. And again, to highlight the point, they're maximizing the eigenvalue. They don't actually care about the eigenfunction. So they're able to use an integral approach because there you don't devote any resources into the interior of the domain. All you're doing is on the boundary. All you're getting is the eigenvalue. If you want to reconstruct the eigenfunction, like for these pictures, then you go ahead and compute the ansatz that you've got using the density. You could use this approach for multiply connected domains. And so there's the Weinstock inequality for simply connected domains, which showed that if you took the first non-zero Steklov eigenvalue, times the perimeter that's bounded by 2 pi. And again, from the survey article of Alexandra and Joseph, there was an example of where this eigenvalue, where this inequality fails. And so we used this as a check to see that our multiply connected solver was making sense. So concretely, what we did was we took um, annuli. So we took one disk of radius 1, and within it we had a concentric disk of radius epsilon. And then we varied epsilon, and we kept track of the first non-zero eigenvalue. So if you compute the difference between lambda 1 times the perimeter minus 2 pi, then you can see that there's a critical point, or there's a crossing over point where the inequality first fails, which is where the radius of the inner disk is approximately root 17 minus 3 over 4. So this bound was obtained analytically in that paper, and what we did here was completely numerical. So if epsilon is bigger than this critical value, the Weinstock inequality seems to work, and then it seems to fail for less. So we were able to compute this critical value, and this is the number we got. So 0.28077, etc. And this matches rather well with the value that was presented in the paper. And then you can use this strategy to play around. So you can shift the center of the inner disk and then see what happens to this critical value. Does it shift? Yes, it does, of course. The solver was also recently used by Oscar Bruno and Jeff Kalkowski to demonstrate that you can find smooth domains for which the high frequency eigenfunctions may not necessarily have nodal sets which are dense at the scale that you might expect. You might expect that, like for the disk at the bottom, um, the eigenfunctions, they oscillate like e to the ij theta. So you might expect that the nodal sets get dense at order 1 over lambda. But they show that if you just perturb the disk a little bit, provided it's still smooth, then you can actually make sure that the nodal domains in the interior don't oscillate that fast. So there are such weird um, perturbations and weird nodal structures in the interior. So another application that um, I mentioned briefly, and one that I'm starting to get interested in, is that of the plasmonic eigenvalues. So in this, what you're trying to do is to compute the relationship between the Dirichlet to Neumann map for the interior and the exterior problem. And excuse me, I think my lambda floats around depending on equation number. I apologize for that. So the Dirichlet to Neumann map can be written down using the modified single layer, for example, times 1/2 minus the double layer or 1/2 plus the double layer, depending on whether you're inside or outside. And then the plasmonic eigenvalue becomes to find lambda and a mu, if you wished, so that at least at the operator level, you've got lambda times the Dirichlet to Neumann map from the interior is the Dirichlet to Neumann map from the exterior. And there's lots of work on this, lots of prior work on the plasmonic eigenvalue problems. And what I've done here is to show you how we can use the operators that we build, because we explicitly build the modified single layer and the double layer. And so all we need to do is to compute the eigenvalues for this eigenvalue problem rather than the Steklov one. And you can do this. And again, you can compute them, for example, on a kite. And you can check how they compare on the left with a disk as you change the kappa parameter, where kappa is a measure, if you will, of the curvature. Here are what some of the low plasmonic eigenfunctions look like on these kites. Here's what they look like, the first few of them as you go from small curvatures to large curvatures. So top to bottom is small curvature to large curvature. Now things get considerably harder on polygonal domains, right? So on a polygonal boundary, the strategy that I described will not work. And that's because as you approach a geometric corner, um, your eigendensity and your eigenfunctions will have some non-smooth behaviors. And so you must use a different approach. And the approach that we advocate is a polynomially graded mesh, whereas Johan Helsing has even more sophisticated quadratures that you can use. And so if you are working with a Steklov-Neumann problem on a polygonal domain, then there's all manners of different singular behaviors you have to account for. So by singular, I mean anything that's not C2, right? What would be ideal and what I'm working hard on right now is to use the work that um, has come out recently due to many people on the seminar again in 2019, which details the asymptotic behavior near the corners of the polygons. So if we are able to exploit what is already known at the analytical level, we can make our quadrature schemes or our graded meshes better so that they capture that behavior, and then we can get higher accuracy. And so on this slide, I show you an example of the kind of graded meshes one could use. So on each segment of the polygon, you could try to cluster the collocation points near to the edges of the vertices. And as you change speed, the clustering gets more and more extreme. So you can test this, and we did. So for example, if you look at the first 6 eigenvalues on a square, then you can compare the eigenvalues you obtain with the eigenvalues, say, on a square of sides 2. And as you change the polynomial grading, you can see that, well, if you take a linear grading, it's not going to give you any accuracy. If you take a polynomial of degree 2, so you have quadratic grading, then your errors go down by to 10 to the minus 3. So you have 3 digits of accuracy in the first 6 eigenvalues altogether. But if you take more and more clustering, so you have the same number of points, but you cluster them differently near the vertices, then you can get higher and higher accuracy.
Nilima, can I ask a question?
Yes.
It's Alex. If you if you're lazy and you apply the C2 method in this context, do you see that it doesn't work in dynamics? Does it get
Yeah.
a big error?
It's actually terrible. So
Okay.
I should have maybe included that, but it's you basically get like 3 digits in the first eigenvalue, and then you get nothing, pretty much.
Thanks.
Sorry, Nilima, Michael, one more question. This seems to be more trouble for the first 6 eigenvalues than the finite element.
Oh,
Because
absolutely.
for the
Absolutely.
first 6 eigenvalues, finite element works.
Absolutely. So
Okay.
um, I wanted to present here A, the strategy, and B, even with this polynomial grading, I don't know if you recall when we were working on the smooth domain case, we had an equally spaced points around the boundary in a certain parameterization sense. And there with 64 points around the boundary, you could get the first 16 eigenvalues down to machine precision, right? Over here, I'm using 1,000 points and a grading of degree 7, and I'm still only getting 10 to the minus 8. So I will not get spectral accuracy. So I'm trying to get as high an accuracy as I can, but I will never get spectral accuracy on um, a square using a polynomial approach, right? So I could ramp up the polynomial degree here, and one could. I have not shown it here. And then one can beat the finite element. All right, so here, just for some, just for the sake of convincing you that I could reconstruct the eigenfunctions, here are some eigenfunctions. And I'm always very um, happy when things seem to work, but then I'm also very suspicious. So in this paper that Michael and Leonid and Yosef and David came out with, they describe these quasi modes that you can compute for polygons, right? And you can compute the eigenvalues numerically, like I just described. And it's very gratifying that the eigenvalues that I compute seem to follow the quasi modes very well. So I've got the first 100 quasi modes and the first 100 eigenvalues, and they seem to line up really well, both for the square and the equilateral. But this is in the eyeball norm. So when I look more closely, then I see that for the square, the deviation from the quasi eigenmodes seems to saturate at 10 to the minus 9. And that for the triangle seems to saturate at 10 to the minus 7. And it doesn't matter how many degrees in the polynomial I use or how many quadrature points I use, this does not seem to shift. In fact, it might get worse or a little better. What's also notable is that some of the eigenmodes are actually highly accurate. And these are reflected in things that have errors of 10 to the minus 15. So this is not a problem of accuracy. What we are encountering here is a problem of conditioning. So the matrices that I obtain using this collocation scheme, they become more and more ill-conditioned. And it is fine to compute the first few eigenvalues, but if you want to go far into the spectrum, so if you want to compute triangle eigenvalues beyond this point, you have to address the conditioning issue. And that's something that I'm trying to do as we speak. But in the eyeball norm, everything seems to work well. So here, there's this graph. You can numerically stare at it and check that this looks like what Joseph and Alexandra presented in 2014. This is for a right angle isosceles triangle. This is for a one-gon. So again, I've presented here very carefully only the first few eigenmodes or the eigendensities, because I don't want to claim that I'm getting the higher eigenmodes very well. How am I doing on time, Alexandra? I should probably be wrapping up soon, hey?
You still have at least like 10 minutes if you go for the full hour.
Okay, I'm going to not go for the full hour. I'll leave time for questions. Okay, so the sloshing problem is even worse, right? So let me be careful. So the sloshing problem could be as bad or worse as the pure Steklov problem on a polygon. It depends on the junction. So if the Steklov and Neumann data meet along a smooth part of the boundary, then the junction between them is at 180 degrees, or it's at pi. And that's where things are really bad. This is at least numerically what we observe. Um, if the junction occurs at an angle less than pi, then things are still bad, but they're not as bad. And so, yeah, it's the same approach as the one I described for the polygon, except here, you're going to get a 0 on the right-hand side whenever your point is on the Neumann boundary. So this makes it a very challenging problem from the discrete eigenvalue solver perspective, because on the left, you have 1/2 plus the double layer. On the right, you have the eigenvalue parameter times a block which corresponds to the modified single layer, and then a whole block of zeros. So both sides have a kernel. And when you're trying to find the eigenvalue for a generalized eigenvalue problem, where both sides have a kernel, you have to do it very, very carefully. And the conditioning seems to really play a role. Yeah, so this is just to highlight the block structure. And on the left, you're going to have something that has a kernel. On the right, you're going to have a zero block. So you can compare what you obtain against some analytic expressions. So this was from the paper, again, of Alexandra and Josef from 2014, where they decompose the Steklov problem on a square, and they show that you can find parts of the spectrum of the sloshing problems on triangles if you look at those of the square. And here you can see that if you use a graded mesh of degree 2, you get basically nothing. Like you get 3 digits of accuracy. You have to go to high grading, but even that is not great. You get 10 to the minus 5 um, digits for your first 4 eigenvalues. So that's not great. And this is speaking to me about the need to incorporate the information that's now in the big monster paper into our quadrature schemes. Here's what happens if you're working on a Steklov-Neumann problem, but the junction is occurring at pi. So you can actually see that at the corners, very interesting stuff starts to happen. And with a graded mesh, you can get, maybe 3 or 4 or 5 digits, but I would not stake my life on the higher eigenvalues. Not yet. But these ideas can be used at the lower end of the spectrum to do spectral optimization, where you try and figure out where to put a Neumann piece. So how long should a Neumann piece be, and where should it be located to optimize a Green's function at a particular pair of points. So this is work that was with Habib Amari and Thema Mary. So I give you a target lambda. So you want to find an eigenvalue that's close to the target lambda so as to maximize the Green's function for the Zaremba problem that I showed on the previous slide. So you want to optimize this object, this G sub gamma sub S. And say for a disk, what I'm fixing is the target lambda and the points x star and y star. And I want to optimize the Green's function at these two, that corresponds to these 2 points by changing the location of the blue segment and the length of the blue segment. And so using the solver that we developed, we were able to show that depending on where you place your points, the gain in the function can be as high as 586 times. It depends very much on where the 2 points are. This is what it looks like. So here's what happens if you have Steklov all around and you have these 2 points, and you're trying to maximize the eigenfunction closest to the target lambda at those 2 points. So if you insert a Neumann piece over here, then you pick up a high value at this point x star, and then you've achieved the optimal gain. You could do the same sort of thing for a kite. And so altogether, we've got a very accurate integral equation approach for smooth domains. We've got something that's accurate for low eigenvalues for polygons. Conditioning seems to be the problem for the higher eigenvalues. I think it's very important for me to understand the actual asymptotic behavior of the eigendensities near the corners, and more than just understand, actually build it into the code. And of course, I would like to go high into the spectrum to probe questions that keep popping up in these seminars about what's happening out further in the spectrum. And the other motivation for doing all of this is to use the approach advocated by Giles or Schmuti on solving Robin problems. You can use the Steklov eigenfunctions to give you a nice basis by which to solve Robin problems with even non-smooth data. So that's it from me. And here are some papers that I think are worth leaving up while I take questions.
Thank you very much, Nilima, for this talk. So do we have any questions for Nilima now? I go on, Alexandre.
So what I'm always wondering about how much can things go wrong if you're not careful, because since I'm not a numerical analyst, I tend to think that I can just plug everything in the computer, it will give me an answer. So before you gave an example where you said you would get 3 digits precision, but can it also be so wrong that you don't even get 0 digits when you don't?
Yeah, it could be. So this is why the papers that are written by analysts are so important in our business, because without, so either we test what we obtain on known eigenvalues, right? Or we need to have some theorems that tell us, okay, the eigenfunction in this situation will have such and such regularity. And then we have to prove a theorem saying that provided we discretize appropriately, we will get this convergence result for functions of this regularity. But from the analysts, we need one or the other. We need either some good, quasi-modes like has recently been done. The quasi-modes are the exact eigenvalue problems, or some understanding of the qualitative behavior, or we need some insight into the regularity. Yeah. But if you don't know anything and you're computing, that's also fine, because after all, you're not going to compute you're not always going to compute a problem for which you know the answer, right? That would be boring. So the approach that I advocate for my students is make sure your code works for problems for which you know the answer. And then when you start to use it on problems for which you don't know the answer, always run a convergence test. So discretize, refine your discretization, make sure that you're converging to in some sense.
Thank you.
Do we have any other questions for Nilima?
I have a quick question. This is Joseph. Nilima, could you please go back to the slide with the plasmonic problem?
I have no theory there. I have to warn you.
I know very little. I mean, I heard about it, but I know very little about it. So I'm just curious. So, yeah, right. So for the disk and the kite, so once again, the eigenvalues are very close?
Well, so for the disk, the eigenfunctions, the first and the fifth eigenfunctions are essentially flat, the constants. Whereas for the kites, they are not.
But did you compute the eigenvalues or computed only the eigenfunctions?
I computed both. I don't have the eigenvalues here, unfortunately. Maybe on the next slide. Maybe on the next slide. Oh, but here I don't have them for the disk. Here they're only for the kites.
And when you said that for polygons, things are do not work, so what exactly doesn't work in that case?
The double layer is not well behaved on polygons, right?
So, right, so you may have essential spectrum and things like that.
Indeed. And so there was very nice work that actually Michael Levitin pointed me to a few years ago by Perfect and Putnar, and then Perfect and Helsing.
Yeah.
In which Johan Helsing was actually doing these very nice calculations for the plasmonic eigenfunctions and eigenvalues for polygonal domains. But I confess I don't know enough about this business here, because the minute you have an essential spectrum, and you might have an embedded eigenvalue, for example. I don't know how to find it because all I ever work with are discrete objects, right?
Mhm.
So as I refine, I might be able to say, okay, this looks like this might be an essential spectrum, but it's very hard for me to say that inside there is an embedded eigenvalue. I don't know enough about this business.
So numerically, say, extracting embedded eigenvalues is is
It's hard.
hard.
It's hard, yes, because um, when I, no matter what I do, when I discretize, I will arrive at a finite dimensional problem,
Hmm.
right? So I will only have a finite number of
Right.
eigenvalues.
Hmm. Okay. Thanks. Thank you.
Thank you, Yusuf, for the question. Do we have any? We have time for some other questions for Nilima, maybe. I have one myself. Again, I mean, I guess it's a theme today in the questions that we don't know about the limitations of numerical analysis and all that. But you spend a lot of. I mean, you claimed a few times that you don't want to say anything about the higher eigenvalues because you don't want to put your hand on the fire for those. But I seem to remember in the last few years that there's been a few results by Eldar, by Edouard Houdet, where they're looking at optimization of Steklov eigenvalues for higher eigenvalues on simply connected ones, and they get these domains with very fast oscillating boundary. They're close to a disk, but with a lot of I mean, I remember the picture is very clear in my mind from
Right.
those slides, right?
Right.
But anyways, my real question, I guess, is why, since apparently you can use these numerical methods to say something about the higher eigenvalues, what is different between these methods and what you're doing that you cannot say something about the higher eigenvalues?
So maybe I'm just intrinsically cautious. So if I had a smooth domain,
Mhm.
right? Or if I were looking at, say, disks and smooth perturbations of a disk, the method that I have using the approach of it's not a new approach. It's quite old actually. This Nystrom collocation approach. It will give you very high accuracy,
Okay.
very far into the spectrum.
All right.
Okay, it's efficient. It's accurate. It's great.
Mhm.
In some sense, it's done, right?
Mhm.
That's not where I'm hesitant to say much. Where I am hesitant to say much is the minute you have corners.
Mhm.
So if you're on a polygon, right,
Mhm.
then we know that this that there will be singular or non-smooth behavior near the corners,
Mhm.
and you have to resolve it.
Mhm.
But the cost of resolving it is ill conditioning.
Mhm.
So if you get too greedy, if you want a lot of eye accuracy high into the domain or high into the spectrum, sorry,
Mhm.
then you're looking to resolve very fast oscillations.
Mhm.
But the resulting matrices are very poorly conditioned. And so when you're computing the eigenvalues at the discrete level,
Mhm.
that's where things go wrong,
Oh, okay.
right? So you have to address, so um, the method of particular solutions is a great example of this conditioning business. So the method of particular solutions was used to compute Dirichlet eigenvalues.
Mhm.
And it fell out of favor because it gave very bad results for polygons. It
Mhm.
had to be stabilized to address the conditioning issue. And that fix came from Nick Trefethen and Timo Betke.
Mhm.
When I worked on the mixed Dirichlet-Neumann eigenvalues, there was the same problem. On polygons, things go wrong. You have to fix the conditioning issue.
Mhm.
And I think a similar fix will be needed here for the polygons.
All right.
It can be done. It's just there are two different problems. There's the accuracy problem, and then there's a conditioning problem. Right now, I'm focused on the accuracy because I'm reading my way through this monster paper of Michael and Co.
All right. Do we have any other questions? Well, If not, let's thank Nilima again.
Thanks.
And let me remind you again that next week we'll have talks on both Sunday and Monday. It's the Young Researchers in Spectral Geometry Special Conference. I hope to see as many of you as possible next week.
Thank you.
Nilima.
Yeah, bye-bye.